Hello! This is the second video in a series about the 3D reconstruction of real objects. In the first video, I gave a brief overview of the project and we talked about image acquisition. If you haven't seen that video, then do check it out. In this short video, we'll talk about building the turntable that I use as part of the big machine. The turntable itself is not very large and I tried to make the design of the turntable as simple as possible. So let's have a look. Let's start with the base to which all other parts will be connected. This is one of quite a few 3D printed parts. On the right, there's a space for the stepper motor. I'm using this NEMA 17 stepper. We don't need very much power in this application, so a smaller motor would probably also work. But I've had this one lying around for years, so I'm happy to finally use it. So if we put the stepper into the slot, then it's obviously not a tight fit. And that's because later I'll want to be able to adjust the exact position of the stepper motor. And to do that, I use 3 M5 screws and nuts. The nuts go into these slots in the base, and the screws come through from the other side. If we now place the stepper in its slot, then we can adjust its position by tightening the screws. And the nuts are positioned to prevent the screws from slipping outwards. Instead of using the nuts, we could also just make the holes in the 3D printed parts tight so that the screws grip into the printed material. That works surprisingly well in situations where there's not a huge amount of force acting on the part. Eventually, there will be a timing belt going to the left towards the turntable. And that timing belt, when it's tightened, will try to rotate the stepper motor to the left. But the positioning of the screws will prevent that. Okay. Let's look at the left part of the base. That's where the turntable will be connected. I've designed it so there will be a threaded rod sticking up from the base, and the rotating parts of the turntable will be connected to this rod. The rod has a diameter of about 6 mm, and I used an angle grinder to cut it to a length of about 87 mm. I don't want this rod to move around. I want this to be fixed in place, because it should be a stable base for the turntable. So I created some slots for M6 nuts. Initially, I thought of using a self-locking nut in the base. Those nuts have a nylon inlay, which creates a lot of friction, so turning the rod is very difficult. Another option is to use 2 regular nuts and to screw them together very tight. This creates extra friction between the nuts and the rod, and as a result, the rod doesn't move. In this case, I chose the second option. It seemed to be the easiest. So if we look at the top here, then there's a round hole on top and a hexagonal cutout beneath it. This is quite difficult to film. It's easier to check out the CAD model. From the CAD model, we also see that the distance between the bottom of the hexagonal cutout and the bottom of the base is 22.75 millimeters. So I put the 2 nuts onto the rod so that the lower of the 2 is about 22.5 millimeters from the end of the rod, and I tightened them. So now the nuts don't move about the rod anymore, and we can push the rod into its slot. The hole is very tight, but I can just slide the rod up and down, although it does require a little bit of force. So now the rod can't rotate in the hole because it's restricted by the lower nut, which fits into the hexagonal cutout. It can still move up and down though, and to prevent that movement, I use another nut on the bottom. Screwing it on prevents any up and down movement. So the hole for the rod is a very tight fit, and there's no noticeable play. If I try to move it around, then I don't feel any movement. Okay, we've got a stable base. Now we want to add some parts to it that can rotate. And first I'm adding this bearing. And if we look at it from the side, then we see that there's a little gap between the bearing and the top of the base. And that's because the top of the upper nut ends just a bit above the base. So the outer part of the bearing, which is the part that rotates, is not in contact with the base. So there's no friction. The inner diameter of the bearing is 6 millimeters, just like the diameter of the rod. However, the rod is a little bit smaller, so it's not a perfect fit. A little bit of movement is possible, but we can very much reduce that by tightly screwing another nut onto it. The nuts only touch the inner part of the bearing, so even though they are screwed tight, the outer part still rotates freely. Now the first thing that may come to mind may be to add the rotating part, add another bearing, and then add another nut and screw it on tight. But if we do that, then our rotating part doesn't rotate freely. There's still a gap to the base, so friction with the base is not the problem. I think the problem is that the two bearings are now under tension from the sides, which reduces their ability to rotate freely. If we loosen the screw on top, then it does rotate freely. But now the screw is not very tight, and there's a risk that over time it will loosen completely, which would allow the rotating piece to move upwards or to wobble around. I don't want that, so I've made the design a bit more complex, but, well, I think it's quite elegant. I'd be curious to hear what you think. The objective is to fix the upper bearing in place with two nuts, but I don't see a way of doing that with this single rotating piece. So I've split the part into a few smaller parts. First, there is this lower piece that has a cutout for the bearing on the lower side and 3 wedge-shaped cutouts on the upper side. That's where these 3 wedges will go. But first I placed the second piece onto it. That piece has wedge-shaped cutouts at the bottom and a cutout for the bearing on top. Next we add a nut and the upper bearing and then another nut. The lower nut should just be a little bit above the upper piece. Now we move the upper piece up and we put the wedges between the lower and upper pieces. They should fit snugly, but not be super tight. If it's not right the first time, then we can take out the wedges and adjust the nuts. I think the best way of doing that is by loosening the upper nut, moving the lower nut a little bit, and then tightening the upper nut again. It may take 1 or 2 adjustments to get it right. When everything fits, then we put the wedges back in and put this third piece over them. And we screw it on so it firmly connects the lower and upper pieces. That third piece also connects the rotating parts with the stepper motor, and it prevents the wedges from falling out. And now all nuts around the bearings are tight and the part rotates freely. Next we connect the rotating parts with the stepper motor. So I put the screws that hold the stepper in place back in and I add the stepper motor. I've also 3D printed a gear wheel which I've put onto the stepper. And that's because the stepper has a square shaft for which I didn't find a suitable pre-made gear. Then I add the timing belt. If the stepper is all the way on the left, then it's easy to get the timing belt on. Now we want to put some tension on it, and we do that by changing the position of the stepper. You can see on the side that the stepper is lifting up on the right, so we adjust the screws a little to make it straight. Just to be clear, we don't need to put too much tension on it. There's virtually no resistance to the movement, and also if we put more tension on it, then the threaded rod will bend towards the right, because I haven't included anything to prevent that from happening. Okay, we're almost done. Next we screw on this plate, and the screws that go through the plate will connect to some nuts that are inside of the top piece of plastic. I added them in during the print. I'm also adding a larger piece of wood and these rings. Those are CCTags, which can be used to position and scale our model when we use mesh room for the 3D reconstruction. To get this to actually run, we have to connect the stepper motor to the electronics. In the first video, in one of the tests, I used the turntable by itself without the big machine. And there I used this setup. Here's the stepper driver, which controls the stepper motor. Of course, we could control the stepper directly, but it's just so much easier to do that with the stepper driver. All we have to do is to send a signal to the driver to tell it that we want to take a step, and it will take care of sending the right voltages through the 4 cables that go to the stepper motor. This particular stepper driver that I'm using here is the A4988, which is cheap, but not that good. Even with the highest micro-stepping settings, it's really loud. In the big machine, I use a different driver, the TMC2209, which is virtually noiseless, and it has some other features as well. We'll see that in the next video. The red PCB is a CNC shield, which we don't have to use. We could connect the stepper driver directly to the Arduino, but it's just more convenient and compact with the shield. On the edge of the shield, there's a connection to a power source for the stepper motors. The Arduino doesn't have enough power for the stepper motor, but even if it did, it's good practice to keep the Arduino isolated from the power supply of the motor. Finally, I'm using an Arduino Mega here. We definitely don't need a Mega for this application. An Uno or something smaller will do, but at the time I wasn't using the Mega for anything else, so I used it here. So the Arduino is responsible for telling the stepper driver when to move, and it's connected to my laptop, which manages the whole thing. We'll look at some software aspects required to run the turntable and the big machine in a separate video. And that's it. If you want to build this yourself, then you can download the STL files and the code that I'm using from a GitHub repository. I'll put a link to the repository into the video description. So, in the next video, we'll look at some hardware aspects of building the big machine. And in the video after that, we'll talk about some interesting topics when it comes to writing software for these machines. Then we can start testing various aspects of the image taking process that may result in better 3D models. So, thanks for watching and see you soon.